The oxidation of butan-1-ol leads to the formation of butanal or butanoic acid, depending upon the conditions used. The boiling points of these compounds are shown in Table 2. In the preparation of butan-1-ol is added to the oxidising agent in a round bottom flask, and the butanal is separated from the reaction mixture by distillation. A. Explain with reference to intermolecular forces why distillation allows butanal to be separated from the other organic compounds. Okay, so when you're oxidising butan-1-ol, you're going to make butanal and probably a bit of butanoic acid as well. So we need to compare all three of these. So let's do these in a table. Let's divide this into three. Let's do butan-1-ol, butanal, and butanoic acid. So butan-1-ol is going to have hydrogen bonding, between molecules. I'll just put HB there so I can use that over here. So butanoic acid is going to have the same. So it's going to have hydrogen bonding between molecules. Now with butanal, butanal is going to be permanent dipole forces of attraction. Which is, so they're my three things. So I've just identified what intermolecular forces exist between all three. So there's one mark if you've got hydrogen bonding between molecules of butan-1-ol and butanoic acid. And there's one mark if you've got permanent dipole force of attraction between molecules of butanal. So these are weaker and these are stronger. And that is your third mark. So just to kind of finish this off, so therefore we'll evaporate first. Okay. So part B, in this experiment, when butan-1-ol is heated with an excess of the oxidising agent, the student obtains 0.85 grams of butanal. The percentage yield is 54.2%. Calculate the volumes, that's what I'm trying to work out, to the appropriate number of significant figures. So I'm going to do the significant figures first. So I've got 3 significant figures here, 3 significant figures here, which means my final answer all the way down here is got to be to 3 significant figures. Just going to give myself a little reminder so that when I get there, I know that's what I need to do. So butan-1-ol is going to make butanal, and I make 0.854 grams of butanal. So let's start with that. So number of moles of butanal is 0.845 divided by the MR, which is 72, and that equals 0.011861. Now this is 54.2%. So in order to get that amount, I've got to aim to make 100%. So number of moles of butanal that I need to aim to make, so this is obviously 54.2%. To get 100%, it's going to be 0.011861. Now if I divide by 54.2, that gives me 1%, and then if I times it by 100, that will give me 100%, and that equals 0.02188 moles there. So 1 mark for that, 1 mark for that. So that's how many moles of butanal I need to aim to make. It's a 1-to-1 ratio, so the number of moles of butan-1-ol will be the same. Now I've got to calculate the volume, which means I need the mass first. Let's get the mass. So mass of butan-1-ol is 0.02188 multiplied by the MR, which is 74. That equals 1.619 grams. Now that's the mass, but to get the volume, if you remember, Volume is the mass divided by the density. So that is 1.619 divided by, and I'm given the density here, so divided by 0.810, and that gives me 2 centimetres cubed. And then down here I've got my little reminder, so 2.00 centimetres cubed to get that final mark. Okay, so 1 mark for that, 1 mark for this, but it has to be to 3 significant figures. Okay, C, give one way of maximising the yield of butanal. So if you remember, what we're doing here is we're distilling it. So let me draw the distillation apparatus so that we can kind of talk about it. So I'm going to have this in the condenser here, like that. My thermometer is going to be here, and I'm going to be heating down here. So normally what we do is we could just put a beaker under there, or a conical flask or something along those lines, and that will end up collecting our aldehyde down here. However, a better way of doing this would be to, if it's not already mentioned, to use a conical flask, because a conical flask stops things evaporating. It evaporates at the sides, it just condenses back in. But on top of that, what you could do is put this in an ice bath and cool this down. Okay, so cool the distillate in an ice bath. Okay, part D. The student adjusted the conditions of the reaction to ensure the major product was now butanoic acid. So for butanoic acid, I need to do reflux, so I need to draw the reflux apparatus here. I've got to make sure that there are no gaps in here when I'm drawing this, and you need to imagine that it is a cross section. So my condenser now goes on top like this, and there we go. The top must not be sealed. Okay, and then water, remember, goes in at the lowest point and comes out at the highest point. So there's 1 mark if you've drawn that apparatus with no gaps. We often find that there are gaps here. People put stoppers in here as well. So with reflux, we don't want any of those. Okay, so there we go. Part E, the 2D representation of the structure of butanoic acid is shown below. State the value for the bond angles labelled A, B and C. So A is around this carbon here, so that's going to be tetrahedral, which is going to be a bond angle of 109.5 degrees. And then B is around here, so that's trigonal planar. I've got 3 repelling areas, trigonal planar, so that's going to be 120 degrees C. And then the example's been really sneaky here. So they've drawn it as if it's a straight line, but if you think of water, that's going to be non-linear or V-shaped with a bond angle of 104.5 degrees.